introduce today's speaker. Many of you know him. How many of you know him? Raise your hand. He is Dr. Nickitas Georgas from Stevens Institute, Philadelphia, New Jersey. To give you a little background on Nickitas, he got a BS in physics, 1966, from the University of Crete in Erlikon, Greece. He got a master's degree in 2001, and he worked on the application of a high-resolution ADSERT model to Stony Brook Harbor, looking at tidal hydrodynamics. And Professor Swanson and I were the co-advisors. His master's thesis is about that. So he's not afraid of work. And in 2010, he got a doctor's degree in ocean engineering from Stevens, focusing on application and skill assessment of the New York Harbor model, which most of us are familiar with, IHOS, ocean prediction model. His general research interests are airstream and coastal dynamics, development of numerical models to forecast hydrodynamics and water quality, and he's known to many of us as a pivotal person in the NIHOPS development and daily forecasts for storm surge and water quality regionally. And so, Nickitas, we're very happy to have you here. The title of his talk today is Novel Numerical Model Applications for Short and Long-Term Environmental Forecasting.
Well, as my wife would say, can you hear me? Yeah. All right, great. I'm very tickled to be here. I mean, like you see, I can see a lot of friends. And in fact, the last time I was here at this hall presenting was 15 years ago when I was presenting my thesis, my master's thesis, on tidal hydrodynamics Stony Brook Harbor. So it's been a while, but I'm very glad to be here. Thanks to Bob Wilson and Larry and people that brought me here to talk to you about some of the work that we've been doing, that I've been doing since I left Stony Brook after my master's. Found a job in a consulting firm for 5 years, and then joined Stevens and became faculty member there after my PhD. So one of the things that have always interested me, and Bob spoke about it, it's how do we actually put in a computer our world, right? It's very hard to do so. And some people would say, well, you need a very big computer, and how correct will you be, right? Well, we're trying for about 10 years down at Stevens to be as correct as possible through a sustained effort to forecast also short-term forecast events, as well as now to more medium-term and long-term forecasting. So this is what my talk is going to be about. And I will be talking for the first part on the more of the short-term forecasting that most of you, or the people that know the New York Harbor Observing and Prediction System that we've developed know more about. And then on the second part of the talk, I will be talking about the more long-term, even climate change kind of work that we do at Stevens, originally trying to use our models and push the boundaries of what we can do with them and understand our world a little bit better. All right, so about 10 years ago, maybe a little bit more, we started building this model called the New York Harbor Observing and Prediction System. It's a three-dimensional general circulation model, so the whole estuarine dynamics are in there, and it's coupled with a surface wind wave model. So we have a wave model interacting with the hydrodynamics. And you see that what we're trying to do is create environmental awareness over mostly the New York Harbor region, which is our major focus. Stevens is on the other side of Manhattan, on the Hudson River, by the way. And but also we include Long Island Sound, we include the Hudson River estuary all the way up to Troy, New York, where the tide bounces back from the Troy Dam. The New Jersey tributaries and the coastal ocean all the way down to Cape May and Delaware Bay. Okay, we're trying to put as much physics over the years. We have tried to put as much physics over the year in our model as possible. So we're forcing what moves the water, right, into those three-dimensional models inside a computer somewhere. There are differential equations that you are familiar with, very similar to between atmospheric science and hydrodynamics. Only our world is incompressible. And we are forcing it with tides. We're forcing it offshore at the offshore boundary with surge and steric effects, with waves. And then a lot of uncertain things when we are doing forecasting for the short-term future, 72 hours out. So we run this model 4 times a day, predicting 72 to 80 hours out, the short-term future, in terms of total water level, includes surges, includes tides, all around this region, as well as 3-dimensional currents, the whole vertical profile at every single point here, salinity, how much salt you have, and water temperature, right? And also significant wave height, regular wave heights that you observe on the beach, and wave period. These are outputs. But in order to get good results for those outputs and good forecasts, we have to put a lot of forces. So we include 239 rivers in our model. And like UTSRC, we have been putting rivers in our model for a long time. Our model is not 2-dimensional. It's 3-dimensional baroclinic. Therefore, it includes the estuarine simulations, circulation that I will be talking about and show you an example later on. And also, we're becoming, maybe most of us become scientists because we want to understand more of our world. And sometimes you get a eureka moment, and you have to celebrate it, right? So about 2010, we started including Hudson River ice cover because we found that it made a huge difference in the tides over the winter time in the Hudson, whether you actually have the Hudson River ice cover providing friction to the tide coming upstream to Troy, changing the tidal range for the oceanographers among you to about 50% of what is normal. Okay? So that was a big eureka moment, looking at the window outside and saying, oh, maybe it snows, maybe that's what it is. And I'm like, oh, well, maybe, yeah. All right. And we've been doing that with one model since 2004 to 2006 when we started pulling out of that application. And one model is not the truth in terms of forecasting. And we know it. And we knew it very well during Hurricane Sandy. During Hurricane Sandy, our forecasts of 10-foot surge were actually 3 foot low. And it was 3 feet low for most of the models that we had here. And when we looked back and saw why, figured out why, it was the wind fields that were adjusting it to that one model that we were forcing and providing forecasts with. So we have to do better with the fact that, and understand, and we did, and understand that we have an uncertain future here with uncertain winds, uncertain pressures, moving our water systems, and therefore we have to understand that uncertainty in the near-term future, right? So with NRL, the Naval Research Lab, we started some work with coastal flood forecast in the face of uncertainty. So now we don't run one model, we run 125 NIHOPSes. And this is just an example of the uncertainty I'm talking about. These are just 96 hours before Sandy hit and came ashore near Atlantic City. These were the forecasts of the tracks from one Navy model, COMPS-VC. Okay? We've looked at other models too. Don't think that this is not representative of what actually was being predicted 96 hours before the fact. It is quite representative. But you can see that some of it have Sandy going up to Nova Scotia. You know that from experience now. You see those wave models all the time. And some of them are going down to Ontario and so on. So you know that there is uncertainty in these forecasts. And if you want to be reliable and you want to explain to the public that this could happen or this could happen, then you have to assign that into the forcing of the model that you are dealing with, the hydrodynamic model that you're dealing with. So we left that old world behind, the deterministic sole model forecasting behind over the past couple of years, and we went into ensemble forecasting. And ensemble forecasting, like Brian Coley is an expert on this kind of thing for atmospherics, the atmospheric modeling. You force your model not with one representation of the possible future, but with as many possible futures as you can. So in this case, we had this NIHOPS model right here, which is the three-dimensional model, and then we nested it over this domain over another model that we created that we call the North Atlantic prediction model. And then because we also include hydrology and river flows, we also are running 125 different possibilities of what the river Hudson discharge could be in the next 72 hours by running hydrologic models upstream. Okay? So we're forcing with several atmospheric, for the atmospheric science above you and the modelers, we're forcing with the GEFS 21-member ensemble, wind and pressure, as well as heat fluxes. The European Center medium, which we actually had to pay for, 51 different ensemble predictions of what the future, the certain futures could be like. The Canadian Center, our short-term range ensemble forecasting system from NCEP, as well as several deterministic members. A full ensemble of 125 SNAP runs providing boundary conditions to NIHOPS, and 125 hydrologic models providing river boundary conditions to NIHOPS. And some of this, by the way, this will be posted, this presentation will be posted. You see, you can find in those three presentations I gave at AMS at New Orleans, a great venue, by the way, for especially for young meteorologists. It's a fantastic venue. If you want to ever go to AMS, it's totally worth it, totally worth the money. Okay. So what that all means is that this is a time series of about 4.5 days, and this is a forecast of surge, of the tidal departure, as we used to call it, right, of storm surge. And this is, the blue one is the tide at Atlantic City, just the normal tide if you have no wind events. And then the red is what was observed on January 10th at Atlantic City, where we had a little surge event, well, that had no name. It wasn't Jonas. It was never given a name, as far as I know. NWS might have a name for it. I didn't know about it. That actually produced higher water levels than Jonas. Okay? And what I'm trying to show here is that the models, all the 125 of them, were basically saying that, well, when I start my model, I have very little uncertainty, but that uncertainty, as the time grows in the future, when I'm here and I'm looking into the future, that uncertainty grows. And though that uncertainty of the tidal departure on top of the tide gives you an ensemble prediction. And that ensemble prediction was able to predict the event in a sense, in a probabilistic sense, by saying that it enveloped the observations at Atlantic City 72 hours before the event. All right, so 72 hours before the event, we were accurate in a way by saying that our ensemble prediction of what the water levels could be is somewhere between here and it was. All right? So if I only had one of those, I would be wrong. But with the ensemble, I can say with a specific range that I'm between those 2 points, probabilistically speaking. All right. And some of you are familiar with this. We actually are cooperating with SoMAS and Stony Brook, and we have this Stevens flood advisory system. Now it used to be the storm surge warning system back in the day when we had one deterministic model only. And we have forecasts for all those stations that we see. If a forecast if a forecasted water level is predicted to go above moderate or minor flood, then those things start blinking. You can go in and you can look at the water levels. You can register. You can get an email in advance whether some place close to you is actually going to flood. And in those, this service now, we also include the uncertainty. We actually display the uncertainty around our model results. Not only the one best solution, the most probable potentially, but the uncertainty as well. And we also have the Stony Brook 9A ensemble member, as well as the NOAA, STOFs, and TSS models for the ones that know what these are. All right, so this is an example of the forcing that we are talking about. This is from COAMPS DC. This is mean sea level pressure, the low system from Sandy. COAMPS DC NRL uses a nested technique. This is sandy right here, as predicted about 96 hours before the event by this COAMS-TC control member. And you can see that it's very good. But I should also let you know that unlike Gulf of Mexico and other places, right, over here we have tides, and big tides, big tidal ranges. And it makes a huge difference whether this correct path, or quite similar to what actually observed path, brings sandy here at low water or high water. That's only 6 hours on an 84, 96-hour forecast, right? So for the meteorologist, you're looking at here and predicting 96 hours out. Well, maybe you'll say, I'm predicting the path very well. That's my metric. I'm predicting my intensity very well. That's another metric. But then I'm off 6 hours. Well, these 6 hours can make a huge difference on the local flooding, right? So it's very important to start realizing that in our region, tides make a huge change. Sandy would have been much more destructive to Upper East River, for example, based on a paper that we wrote, if it had hit about 7 hours before it did. There's nothing to say that Sandy couldn't have hit 7 hours before it hit. All right? So this is the kind of storm surge forecasting we're talking about, but then we want to take it a little further. This is a 6 foot by 6 foot grid that shows how Sandy flooded the New Jersey waterfront. Stevens is right here. This is Manhattan Island. We're up on a high hill. And I just want to play it one more time, if I'm allowed, to show you how those grids that now go over land, right, can show where we're vulnerable, first of all, where the water first comes in from, right, and how much water you actually can have on your streets, rather than a station with some water level at some point, like what I showed you before. This is where we really want to go. We want to go to the maps of inundation above ground, so that you know, and we all know, and I know, I want to know too, that I'm going to have that much water or this much water where I'm standing.
So Nickitas, you never showed the New York side. Is that
We did. So this New Jersey Waterfront, by the way, this is published. You can find the paper online. The New Jersey Waterfront model is only including the New Jersey Waterfront. That's why it's called the New Jersey. The Manhattan side is not, but it's linked, again, nested within NIHOPS, right? So it's not that we're not solving the New York side, but we are forcing the land part and the very close to shoreline part on a very high resolution grid for the New Jersey side only. And we do that for a big project now for the Port Authority of New York and New Jersey. All right, so I spoke a little bit about hydrology. That's very important. The rivers are coming into NIHOPS and can produce flooding of their own, right? There are two types of major flooding events, right, that affect people. It's the coastal flooding and the surge during a hurricane. And then you have the other side where the river is coming up and flooding, bursting its banks because of precipitation events. And then what happens when those two things are happening at the same time, right? What happens when you have a surge from the ocean that inundates your coastal plain, and then you also have a river that's flooded because of precipitation at the same time? Well, we know that this happened during Irene. Before Sandy, there were a year before that was we had Irene, and we had huge flooding up north in the Hudson, near Albany, for example. All right, so like I said, again, little things in a computer model can help. We are predicting hydrology and flooding and discharges all around now the Hudson River watershed, including the Raritan Bay watersheds, Raritan River watersheds, Passaic, and Hackensack. What flows come in depending on the precipitation from those global models, the ACMW, the European models, the NCEP models, and so on. So 125 different possible discharges that can come into our NIHOPS receiving water model for the tidal hydrodynamics in the Hudson and New York Harbor. How did this hydrologic ensemble do? These are 5 different stations: Hudson River at Fort Edward, Mohawk River at Cohoes, Wappingers Creek, Hoosick River, and Hackensack River at New Milford. The red, if I'm not mistaken, is simulated. Yes, the observed is black. This is Hurricane Irene. So this is a validation of this model for river flows during Hurricane Irene. And you can see that, for example, Mohawk River jumped from about 10,000 cubic feet per second to about 120,000 cubic feet per second for that event, about 12 times or 100, yeah, something like that. Very big jump. Okay, and we are able to calibrate the model, and now we're running it all the time. NOAA is doing something similar. They also had one deterministic model called AHPS, Advanced Hydrological Prediction Service. You can go online and you can find the forecasts. This is one event, one station. In December of this past year, maybe a month ago, this is what AHPS was saying. This is what all our ensembles were saying for this particular station. This was below minor flood level, but regardless, you can see that for this event and that station, AHPS was off. I think there will be the HPS will be off today as well, from what we see. NOAA understands this. They understand they have to go to ensembles. They go to ensembles. They've gone to ensembles for storm surge, and they have that impetus now to do ensembles for storm surge. But they also are starting to do hydrologic ensembles as well to exactly envelope that uncertainty. And that uncertainty for rain, by the way, we know from experience is much more than for winds, unless you have a hurricane. But rain, it's very hard to predict. We know from experience again over the next 24 hours even. Jonas, we were looking at the models. Just again a story. We're looking at the models from Jonas. About 24 hours in the past, before Jonas, maybe we're looking about 10 inches of snow at most. Well, we got about 30, right? So that is certainly something that requires a lot more research. How do we create better ensemble or better predictions for rain and precipitation in the short term?
Can you comment on the figure on the right?
Yeah. So the figure on the right, and I'm sorry about this, but I just want to show you. As I said, we're running 125 different precipitation fields. This is the Sutcliffe coefficient. Basically, this means it's very good. The model is very good, or that ensemble member in this case. The y-axis is every ensemble member we run, different precipitations. This one means that the model is almost perfect, and this means below 0, actually below 0.7 or 0.5 means that the model was not really good in terms of predicting discharge at that particular station. And I think that's Rondout Creek, upstream in the Hudson, one of the tributaries. So you can see that the GFS deterministic, for example, was very good. This is the median hydro NIHOPS, that blue line. ECMWF was close in this case. AHPS was up here. There's the ensemble control for the ECMWF and so on. So we're keeping track. Because at some point, I wouldn't like to run 125. Maybe I can run 50 best over 125 and conserve some resources to do something else. Right? So that's one of the reasons that we're doing this. So I spoke about Irene. Unlike ADCIRC, unlike several of the models that you see out there that are fantastic for storm surge, and I was working with ADCIRC 15 years ago with Bob, and basically when it was starting, and now it's one of the best models we have, really. But it is still two-dimensional for the most part. It's not baroclinic, although some baroclinic applications have started coming up. And it's hard to include rivers. With NIHOPS and the scope that we have, we actually can include rivers. This is a fish tank kind of view. So you're looking at the Hudson River from Verrazano Narrows Battery all the way up to Troy Dam. And what you see here is currents. Here the blue is fresh water, and the red is ocean water coming up from Verrazano. So you're seeing the Hudson as you would see a fish tank. This is the bathymetry. This is really where the depth is along that Hudson transect. And this is temperatures, all right? These levels here, and I know some of you have seen this plot, these levels here are flood levels across the whole 150 miles of the Hudson. So if the water levels are going above here, then something is flooding, right, along the banks of the Hudson. This is a whole tidal river. The tide goes back and forth.
What's
So this is about, this is meters, depths in meters. So it's about 4 meters or so up there. And let's see what happened during Irene and why I'm saying that it's important to include those rivers. This is the surge up in Buttery, the August 28th. And then you see this? This is all riverine flooding all the way up to Albany and Troy. You see the pictures. If you can Google the pictures, you can see the flood plain was basically inundated with waters. The other thing you see, if you study this on your own a little bit, you basically see that the freshwater that came above Troy Dam pushed all the salt out of the estuary, all the way down to almost the Battery, as you can see here. The river became a river, a real river. It's an estuary, and basically during Irene became a river, a freshwater river for the most part. It's a river that Native American, the word I can't pronounce, but it basically means the river that flows both ways. For a couple of tidal cycles during Irene, the river was not flowing both ways. It was not a tidal river anymore. The whole discharge that came out from Mohawk and the upper Hudson basically pushed the tide all the way out of the estuary and flushed it out. And we have data, by the way, that have explained this, and we have seen we picked up some rise in temperatures over here, observations that came down from the Indian Point Power Plant area as it was advected south of this blob right here actually came down and was the only place with observations along the Hudson that during Irene the temperature spiked rather than decreased. So the models can help our understanding. Okay, we don't know everything. Like I said, for about 3 or 4 years before I put ice in the Hudson, I was wrong when we had ice in the Hudson. The models were wrong when we had ice in the Hudson. But then we figured it out. We put in the model. The models are better, right? Because we can mix the salt water and the fresh water effectively with our model, we can actually predict, and again going through applications, we can actually predict where the salt front is throughout the Hudson. And this is the Hudson right here. This is a scale of the Hudson, and you can see where that salt front, where that salt from the ocean can reach all the way up to about river kilometer 124 is Poughkeepsie, the drinking water intake. If it reaches there, they have to shut down the valve, right? If salt reaches there, it's toxic for people. So we are actually predicting this, and New York State DC, for the past 5 years, have been tracking the model and how it has predicted that mixing interface between salt and fresh water in the Hudson, and has been using it for the last 2 years specifically for sturgeon sampling in the spring, and have found that, yes, this little computer thing running somewhere is 15% better than USGS database statistical model that was tracking the salt front in the past. So this is a first, as far as I'm concerned, on how those models can actually do in mixing those water masses, right? We were actually able to predict with 15% better accuracy compared to observation-based statistical models where that salt front is. All right? And very quickly, you can go online. There's a website. Some of you are familiar with it. But we also send our forecasts to the Army Corps of Engineers. We're sending them to the Coast Guard for search and rescue, and also the ORNR, the NOAA Office of Coastal Restoration, because we know where the currents are, right? So if something happens, they can track where something can potentially end up, or run our currents backwards and try to figure out where it came from. So in our forecasting, you can get the flood forecast, but also this NIHOPS traces service, and basically you can just follow the directions, get our currents, and then play with them. And it's a very good exercise for students specifically because they can load the currents, they can visualize them based on some tool that's also available on the website, And you can see how when you put something in the water, can also advect, but also disperse based on our models. All right? So you see the influence of the tide. You can change the winds, and you can play with the current, and you can see where things can end up. Okay? So it's very, I find it very easy to explain to students how advection and diffusion works that way in a coastal environment. And then we do some work like that for DEP by also coupling our model with a fecal coliform and an anthropogai model for water quality. So we can actually predict or at least tell them when to close the beach, not to close, when to issue an advisory, when to issue an advisory for a beach, for primary contact recreation, for example, or a water body advisory that they do based on different pathogen standards that they have for the receiving waters around New York Harbor.
So do you use the New York City discharges for that?
Yes. Yes. We're coupling with their hydrologic models, so it's not the HMS big discharge watersheds, but they are the urbanized watersheds of New York Harbor, depicted by hydraulic models. Yes. And to the second part of the talk, now we leave this short-term forecasting, and we will talk a little bit about the more longer term, okay, and the predictions in terms of climate change and so on. We had a project with the Long Island Sound Study, EPA Long Island Sound Study, through New York Sea Grant, which is right here, and Connecticut Sea Grant jointly. And basically what we wanted to see was there has been a lot of interest in the changes that are happening to Long Island Sound in terms of responses of fisheries and changes in the fisheries. There has been a noted regime shift in Long Island Sound where cold species are moving north to Gulf of Maine, and warm species from south of our region are moving into Long Island Sound. And that happened right about 1997, 1998. That's when it was first seen. 10 years later, they could actually see something changed in Long Island Sound fisheries. Okay? So we want to see, and there are other theories that say that this is basically primarily due to thermal habitat considerations. These are warm-blooded animals. They respond to temperature fluctuations. Fish, right, respond to temperature fluctuations. And therefore, there is a thermal habitat that they have been accustomed to. And when the conditions change for them, then they either have to move or die, or because of stress, right? So we had this model, and EPA said, well, why don't you run it from 1979 and see if you saw anything? Did anything change in temperatures? Did anything change? Can you tell us something about Long Island Sound over the last 34 years? Right? And that leads to near-term projections as well as longer-term projections. So yes, we did run the model, this Nyhop's model, the whole three-dimensional hydrodynamic model, from 1979 to 2013. And then we compared. We, of course, had to validate it for 34 years. That's a lot of data. We had data from observations at stations from the Long Island Sound Survey, Troll Survey, from Connecticut Deep from 1990 to 2013. We validated the model against those data. And also validated the model against the what's called the climatology, which means basically if you put all the data together from the World Meteorological Organization data or the NOAA fisheries data and all the temperature salinity that you have for Long Island Sound over the years, and you take the mean January, that's your climatology, that's your mean January conditions. If you have your mean February. Rutgers had done this for us. They have created a data set called MOCA 2.0, which basically on a grid shows you what the month of January usually looks like over the whole Long Island Sound as well as the Mid-Atlantic Bight, which we call MUB.
For what variables?
For temperature salinity. Three-dimensional though, right? All right, so we forced our model similarly to usual, but because we're running now in the past, the best data sets that we had to force on the winds and surface heat flux and so on was the North American regional data set called the North American Regional Reanalysis, which basically brings in all the models and the data together, the observations together, and creates fields every 3 hours from 1979 to now of what the winds were, the pressures were, the heat flux variables were, temperatures were, and so on. USGS gave us daily reconstructed work on that, river discharges, what our rivers were doing over these 34 years on a daily period. And then for the offshore boundary right here, we have a data set called Simple Ocean Data Simulation that's run at Texas A&M and UMD, University of Maryland, out of that provided us with temperature salinity profiles at the offshore boundary to close our model. Okay? And how do we do when we did this? Well, first of all, I want to note that this data set now has 34 years of nor'easters and hurricanes in it, right? Because we're forcing it with historic data. This is from January of '81 all the way to October of 2013, the storm surge or the tidal departures predicted by the model in blue and the data in red for a lot of different events, from Gloria to Floyd to nor'easters of 2010, 2007, so the whole shebang, right? And this is how we did in terms of validation. This is a correlogram. There's the observations. There's the model. One-to-one line means perfect. These are water levels. This is Sandy right here. So we underpredict Sandy because, again, we're running one deterministic model based on 3-hourly data. But not horrible. It's very close to what the data were showing for the battery in particular. That's one kind of event that we have in this model. Because it's an estuary model, this is surface salinity, this is surface, again, salt content. You see the blue, again, is fresher water. This is the Connecticut, Quinnipiac, and Cohocusatonic River, right? Coming out at the surface. This is the bottom. What you're seeing basically is the progression over the years of monthly average fields out of that model that was running basically every day, right? That's the mean salinity across the water column, and then that's the stratification. And you can see how, as the plumes come out of those rivers, are stratifying the waters in terms of salt stratification, right? You have fresh water on the top and salt water on the bottom, and you can see the events happening. And now you start picking up some of the Connecticut deep data along that transect, that central transect. Thing to note here is that these are monthly averages, while that the model is providing here in terms of surface, mid depth and bottom, and the data are once every whenever they came up. But you can see that the models are tracking very well that this part of the sound is fresher, and this is saltier, and also the dynamic evolution of the whole 34 years in Long Island Sound's history, right? It's a model, but how good is it? These are all the data from Connecticut Deep against the model. Again, correlograms. You can look the usual metrics, root mean square error. Practically speaking, we're off by about 1 degree Celsius. Well, you have from 0 degrees Celsius to 30 degrees Celsius variations in temperature. 1 degree is very small error, but it's still an error, right? And this is for salinity for the 3 basins of Long Island Sound. The model is not perfect, for sure, but it's definitely better than climatology, for example. I don't know how many of you have dealt with this kind of plot, but this is a Taylor diagram. Basically, this is where the observation standard deviation is. This is where you want to be as a modeler, as close as possible to this point for temperatures, and as closer as possible to this point for salinity. This was the climatology for temperature. The model was closer. This is the climatology for salinity. The model was closer, split basically in half. What you see here from, I know that Brian Coley basically taught me this Briar skill and Briar skill score and all that jazz. But basically what you're trying to say is, how is the model doing again against climatology? And the closer you are to that 0 line here for temperature and that 0 line for salinity, the closer the model is to perfection. let's say, right? And this is climatology, worse for temperature, and this is climatology for salinity. Of course, for salinity, it's going to be worse. We know that because there are a lot of more events that contribute to the deviations from climatology. So the climatology here is not a good predictor of what's going to happen in Long Island Sound salinity at all, right? The model is much better. You also see for temperature that 2012, which was one of the last years we had, was an extremely not well predicted model, just based on what usually a usual year would be. It was very, very, very hot, right? We know that. So that's what this shows here. But the model was able to actually capture that heating because it was down here. And to the edge of List, this Western Long Island Sound, there's some results I put together for one of the stations there in terms of temperature, surface and bottom, over 4 years, and the salinity. At that DEP station, New York DEP station, not Connecticut DEP. The model hasn't drifted over that whole 34-year simulation. This is a histogram, if you'd like, a bar chart of the errors from minus 2.4 degrees Celsius to minus 2.8 degrees Celsius over the whole spring survey from Connecticut DEP, right? With most of the errors being within 0 degrees. Minus 0.2. So very close, very good results. And it hasn't drifted in time. That's important to know. Because if we're starting looking now on trends and capturing trends, we want to make sure that when we started running the model, it was doing well. And 25 years later, we're still doing well. Because otherwise, we don't have a good prediction of what actually is happening over the whole season, the whole seasonality. So this is how the model was doing at Millstone. This is the longest record of water level temperatures, of water temperatures we have at Niantic Bay, at the power plant, near the power plant. The observed anomalies, if you'd like, the departure from the climatology, are shown in red, and the model is shown in black. And you can see that the trends are within the same statistical significance, about 0.4 degrees Celsius per decade. That's how much warmer Long Island Sound temperatures are getting. For the last 34 years, they have been increasing by about 4.4 degrees Celsius per decade. Okay? But only from 92 to 2012, which was a very big concern for Long Island Sound scientists, we were actually getting 0.72 trends. If we just don't start looking at 79, but we look from 92 on, we're jumping about doubling those trends, right? So what's happening? Well, it turns out that the percent of bottom temperature variability explained by air temperature, bottom temperature in Long Island Sound explained by air temperature alone, is 80%. The sound is, for the most part, a lake forced primarily in terms of heat by downward heat fluxes and upward heat fluxes rather than advection. 80%, this was done with wavelets, by the way, 80% from 1979 to 2012 is forced by what's happening in the atmosphere. Locally forced. It's a lake. It used to be a lake. Well, comparatively, it's still, in a sense, a lake. Maybe about 20% of it is coming from other sources, but it's still a lake. All right. So that, if it's forced by the atmosphere primarily, then what's happening? That's the question, right? That's the question we have. What is happening now? Why did we have those situations where for the last 20 years it seems like it's warming much more than it used to? So we started looking at teleconnections, the science of the connectivity of the global atmosphere and how that translates to local effects. And instead of looking to the Atlantic, which is our neighboring ocean, we started looking at the Pacific, which is our not neighboring ocean. There's a whole continent between us, but atmospherically speaking, it's upstream of us. And things are coming from the Pacific over here. And what we found, long story short, is that the Pacific is a major contributor to what you are actually seeing in Long Island Sound and the Northeast. It's not the NAO, it's not the North Atlantic Oscillation, and things that are happening in the Atlantic for the most part, but it's mostly related to what's happening in the Pacific that you actually see signals propagating here. All right? a positive phase of the Pacific decadal oscillation means cold temperatures in the Central Pacific, warm temperatures in coastal California and Oregon, and cold temperatures in the Long Island Sound. Actually, you can even see it here based on J-cell. And the negative phase is warm in the Pacific, cold here, and warm in the Long Island Sound. So negative means positive, warmer than usual for us. This is what I'm talking about in terms of downstream. What happens, for the meteorologists, what happens is this is a correlation between 500 hectopascal geopotential height and the PDO index. Basically, when you have a positive PDO phase, the jet stream dives in and you have colder. Positive PDO means colder waters in Long Island Sound. So then we looked if the PDO is important, and that's what we hypothesized. We're not the first. There were definitely links that are documented for the Pacific region, for salmon and so on. And also some work from Wood and others in Chesapeake Bay regarding the PDO. Then we started looking at the whole time series of the PDO index against surface temperature. And what you see is just by looking at a linear R square, you have an R square of 0.31. Those two covary. And it's better to see the index that reflects the phase of the PDO and what's actually happening in Long Island Sound, covary. And this is a better way to see it, where this is a cumulative index and cumulative anomalies for the temperatures. And you can see that before 97, the regime change that we spoke about, you had more positive PDO anomalies and also more negative SST anomalies, colder waters. After 97, the PDO changed phase. It's documented. The PDO changed phase, you have more negative PDO anomalies, more positive SST anomalies. So in a sense, the positive PDO era until about 1997, there are more years with colder than average water before 97. And after the PDO change phase, in 1998, the negative PDO era, more years with warmer than average water. How am I doing with time? What's the...
It's got 10 minutes.
Perfect. Okay. Perfect. All right. So the PDO is an important, and the Pacific, and we just started scratching the face of this, right? We're looking at other indices. We're finding very interesting results, and there will be more coming up for the role of the Pacific to our regional waters. So now what's happening in the short term or the near term, right? Well, guess what happened after 2013? The PDO changed phase again. Now we don't know. The PDO is about, the periodicity of the PDO is about 10 to 20 years. It's unpredictable. And we don't really know what's causing those warming, that warming or cold temperatures in the Pacific, right? We still don't know that as atmospheric scientists. But the PDO started becoming positive again. Remember before 97, right? It started changing phase. So now we have colder era again. We don't know what's going to happen if that shift is permanent, but we definitely see a PDO that's positive now over the past 2 years. All right? Positive PDO, colder temperatures. This is November 2015, this past November. Why am I highlighting that? I'm highlighting that because if you do lagged correlation, I'm not going to go explain this graph, it's crazy. But basically what that says, wherever you see a really high magenta color, that means very good correlation. And in this case, it means that there's a high correlation of about 0.8 correlation between the November PDO index, what happened this past November, and the next June, bottom water temperatures in Long Island Sound, based on the model. Based on the model, on our model, right? Because the bottom water temperatures in Long Island Sound are not known. We had to reconstruct that history, right? Okay, so then what does that mean? That we can potentially predict, what the June bottom water temperatures would be, or the deviation, right, for next summer in Long Island Sound. And that's the temperature outlook for the bottom waters of Long Island Sound. There's the trend over the years. I think the R square is about 0.5. Huge R square for climate. For climate, this is very good R square. 50% of the total variance is explained by a PDO alone. For the November PDO explains what summer, the next summer's temperatures are going to be. And because November was around 1 of the previous November PDO index, we're expecting colder than average water temperatures. Now there is scatter, right? There is scatter, but I don't see anything in the recent past that was up here. And in any case, that could mean bottom temperatures in Long Island Sound will start getting colder, right? That's the prediction at least. All right. And now what about fisheries, the link to fisheries? If, like scientists are saying, if the temperatures control the fisheries distributions and the shifts, then there should be a correlation from PDO, which controls the temperatures, hypothesis, right, to the fisheries response, right? Well, Penny Howell from Connecticut Deep has basically created a way of looking at fisheries in general by putting some of the non-directed fisheries, basically the fish that are not fished, they're not taken, right? The natural variations. The cold fish and the warm fish, the ones that like cold waters and the ones that like warm waters, right? And guess what happens? These are the cold temperature species, and this is what is called a habitat suitability index. So what's the temperature of the water that is more suitable for the cold species in the spring, okay? And you see that about 11 to 12 degrees Celsius is, for that conglomerate of species, is the best habitat for them. And then it basically declines when it's colder or warmer. Over here is the warm temperate species, the warm blood, the ones that are warmer, that like warmer water. And it's almost a monotonic increase in temperature to 18 to 19 degrees Celsius. That's what they like most. But then they fall down when it's colder waters, when the waters get colder, right? They don't like that. Well, guess what? This is actually an R of 0.75, a correlation between the previous summer PDO index, Pacific, and the weight or tow anomaly of what the Connecticut Deep is actually surveying in the spring, right? So you're looking at the PDO in the summer, and the data here show what the Connecticut Deep over the last 35 years has been, 25 years has been collecting from the troll surveys from the Sound in terms of warm yield. All right? So what happens? Positive PDO, colder temperatures, less than average tow of fish grabbed from Long Island Sound. Negative PDO, warmer temperatures, more than average warm yield species in Long Island Sound. R of 0.75, pretty crazy, right? So it does explain the PDO alone, and forget now the model. We took the model out. We just used it to find something. Now the model is gone. This is just data, just observations. What about the spring cold yield outlook? Now that's not a good R square. It's 0.43. Scattered a lot. But again, the functional relationship is the same, or opposite sign now, because these are cold species. The cold species in higher PDO years, colder temperatures, they are better, they will grab more than average. Colder PDO years, negative PDO years, warmer temperatures, less than average. Yeah. So there is, yes?
What is CL, remind us? You got R equals 0.43 and you got CL.
The confidence interval. It's a confidence interval, right? And very briefly, so now we can say that based on those functional relationships, maybe we can start saying to Connecticut Deep how much fish they're actually going to be getting out of those troll surveys, right? So we're starting something that's a fisheries outlook, right? The University of Maine does something similar for lobster, by the way, and we've looked at lobster in Long Island Sound, but I don't have time for that now. If you want to ask me for explanations about lobster, I'll be happy later. What about the long-term future, right? Global warming, two very different scenarios of global warming. This is CO2 concentrations from 2000 to 2100, about double CO2 concentrations, carbon dioxide, based on the representative concentration pathway 8.5 scenarios, and an increase in the global temperature of 3.5. If temperature and the habitat controls, then we're talking about a very different future for the fish as well, long term, right? So we coupled NIHOPS on a projection mode with a IPCC caliber model called CM2.6. And basically the main picture of what's happening based on a 2 times CO2 increase in the next 70 years, 1% per year annual increase in CO2, or CO2 equivalents, I should say, is that the Gulf Stream will actually move up closer to our waters, making our offshore boundary right here warmer and saltier, right? And the temperatures would increase quite dramatically. Forget where we're trying to go with the Paris Agreement. The Paris Agreement is saying 1.5 degrees to 2 degrees Celsius, right? That's what we're trying to do, 1.5. Well, I think it was globally average, the anomaly was 0.9 in 2015 or 0.7, I don't remember. But we're halfway there already, okay, before the 2 times CO2. Anyway, I'll skip the assumptions of the model. Unfortunately, I don't have time to go to it, but I'll be glad to answer questions later. This is what we're looking at based on projections of the next 80 years if we increase by 1% every year. We're talking about a total climate response, a transient climate response by the end of where we reach 2 times CO2 of 2.6 degrees Celsius higher temperatures for surface air temperature over Long Island Sound, not 1.5 or 2, 2.6. The sea surface temperature at the self-break, 2.6. The bottom temperature at the self-break as high as 3.8. And over Liss, we're talking about 3.7, 3.9 degrees Celsius warmer. Okay? In SST, 3.9. In bottom temperatures, about 3.7 degrees Celsius warmer. Now, I want to say that on the record, these TCRs for Long Island Sound, I believe, are likely overestimated due to the lack of variability in wind forcing. We use monthly wind forcing, and I believe this is a very bad thing to do on models like this. We run with 3 hourly operationally, we run with hourly, whatever. Monthly wind forcing is the effect of wind forcing is nonlinear, both for latent and sensible heat fluxes. With monthly wind forcing, you're underestimating the variability of the winds and their effect, especially in wintertime, the cold season, and therefore we are probably overheating the Long Island Sound in this projection. So I want to point that out. But whether we reach that in 70 years, or we do something about it and we don't reach it in 140, this is a very different future, right? And this is for fish gills. Again, what happened between 98 and 1999. Unfortunately, I don't think I'm going to have time. I want to close it here and open it a little bit on questions. But basically, what it says is that if you start, based on that model, counting the percent of area time days that is preferred for neither of the two gills, we first see large decline because colder temperatures are no more. They're all warming up, and all the cold temperatures are going away. So both species will, the percent of area that is not good for any of the warm or cold species will decline. That's a good thing, right? We have more area potentially for both species, for both gills. At the same time, the warm gill only, the percent area times days preferred for the warm gill increases threefold. Okay? So the South Carolina fisheries are coming up here, right? The warm gill is moving up threefold. And the percent area times days preferred for both gills, also important, increases by 1/3. So the time where both worm and cold fish are at the same time competing for resources in the sound increases as well. So increased competition, more worm species coming up, or at least the thermal habitat is suitable for them, and and that's basically. And that's where I'm going to leave you. So I hope I took you to a very long, broad story, but again, we can do this now with models because we're putting more and more and more physics in them. We have bigger computers, and we have much more science coming into that. Even statistical tools, forget the numerical tools, even statistical tools are getting much more complicated than they used to. Wavelet transforms and so on. You can go on MATLAB, you can download all those things, you can apply them from steric effects and sea level rise to anything you want. You don't have to just look at fisheries. So it's a very good place to be. A lot of tools that you can start answering your own questions locally, and potentially trying to figure out the global details and teleconnections of those patterns. And I'll leave that. You can read the conclusions. But
Thank you for some exciting this. So do we have a few questions, Mary?
So you had to take chemical oceanography. Have you thought about adding oxygen to this?
Yes.
Because the fish bottom
Absolutely.
temperature is going to be a big, the fact that water is warm, if there's no oxygen, they won't live there.
Right. No, absolutely. I mean, saturation effects are important, but more than saturation effects, hypoxic events are more important too. And that would require, of course, putting BOD in there. Excuse me. We've done that in the past with other models, with water quality models, the system-wide eutrophication model and so on. But yes, we would like to, now that we have the hydrodynamics, and I feel excited and very good about the data set we've created for the hydrodynamics, I want to put a water quality model coupled to that, so that we have the whole biology. You have the DOC and the phosphorus and the nutrients and the whole, and then carbon cycling and DO, which is really a very important aspect. But isn't it amazing that 50% of the variance is only temperature? It's crazy.
But temperature is related to oxygen.
That's true too. That's absolutely right. And also, the spatial variability has the spatial integration over the whole map is also important too, of both of those variables.
The Pacific Decadal oscillation has 40 to 50 years oscillation, and in your statistical model, how long do you use the period? It seems to me you only use half of the period.
We use what we have. We use from 1979 to 2015 now in newer results.
So it seems to me that when you compare the PDO index with the temperature, it seems to me that you use it seems to me there's just a warming trend rather than the PDO oscillation.
Yes, good notice. Yes. Well, we know that there is a warming trend. And the PDO, you're absolutely right, the PDO does not include global climate temperature increases. From the PDO analysis, the indices of the PDO, you take out the trend, you take out the global temperature trend. It's not in there, right? So what you see is an increase because you had a negative phase to begin with in that specific area, and then a positive later. You're right. But you also see that something changed when the PDO changed. And that's what I'm trying to say, that the PDO is controlling. It's not the functional relation. Yes, we're right. We don't have, actually, it's 20 to 40 years periodicity, right? 20 to 40 years. It could be 2 cycles or 1 cycle. But, so I'm not trying to explain why the PDO is like that. What I'm trying to explain is that the PDO has a statistically significant correlation with what's happening in the fissures of Long Island Sound.
Just sticking with the PDO, you made a forecast for the spring, right?
Yep.
So physically, what's happening to the water column that's going to cool it off? I mean, what's the scenario here that's happening locally? I mean, in terms of fluxes or mixing, or I mean, you're making this forecast here for cooler waters, and so we're halfway there.
I have no idea. I have no idea.
Okay.
All I can say is that I hope that this correlation over the last 35 years can explain the 50% variability that we're looking at. But it's still 50% variability. And in fact, in terms of the annual, it's only 30%. The R-square is 30% variability, right? So I don't know what's going to change in the next 2 or 3 months to go to a colder temperature.
The only reason I brought it up, I mean, it could be a very useful tool, but if you're communicating with the public or whoever, and you're going through this seasonal forecast, you probably want ways to kind of understand now that we're in January, February,
yeah,
how things
and I
are
hear
going.
the
And so,
bird chirping.
So that's always my concern with some of these statistical approaches is that you give an answer, but you're not quite sure physically what's going on.
Absolutely, you're right.
Paying this first and then
But I have to say before that, just stay in touch.
Yeah, okay, very relevant one. Also about this PDO temperature relationship. Do you have any estimate how much actually the temperature change is due in terms of degrees?
Yes, we're looking into that right now. Yep.
Something. I think Jaime said before that it's really questionable that the approach you here is correct, because you basically have a period that just one phase change PDO around 2000. So you're trying to do month to month and even year-to-year change doesn't really mean anything. The PDO is much longer time scale. So you really try, when you get high correlation, just because it's phase change. So when you try to make a prediction, say from one summer to one spring, you try to say the real correlation high just because there's only one phase change of both record.
Mm-hmm.
And then now you try to push very hard, try to go into say the previous spring to this winter, you sometimes say, but you're really basically all along the long record and not really short variation.
I want to make sure that we understand that this is, because I didn't mention, this is ranked correlation, Spearman ranked correlation. It's not a linear correlation coefficient that we're talking about.
So it's really a problem. And part of the reason why you have a temperature, I would bet, in your forcing, you have this term that people curve that adjust the surface temperature of ocean seawater to the atmosphere temperature. That's why we go high so high. So it's really part of the artificial effect. You're not really driven by the real heat flux from the atmosphere. So I think the effort is good, but you have to be very, very careful because of this. People use PDO for all kinds of things. But, the record is really very short. And so one has to be very careful about this kind of thing.
Right.
Malcolm, then maybe.
Thank you for a very interesting talk, Nickitas. Just a little story and then a question for you. The little story is, during Jonas, my daughter Sally parked her Toyota minivan, nice shiny new minivan, in Main Street in Hoboken. Woke up in the morning, the surge had come up, the sewers were backed up, and her van was full of raw sewage. Okay? So it's a sad story. It's a write-off. So you're a very progressive mayor in Hoboken. And the question is, if she calls you up in the middle of the night before a storm comes, she says, Nickitas, what's the flooding going to be in the main streets of Hoboken? I mean, how confident are you in telling her, in other words, getting down to the street-by-street level? It kind of worries me because, as you know, storms can make a sudden twist or turn the last few hours. So, you showed that nice map of the flooding Hoboken.
Right, yes. So we're trying to do that with the uncertainty in the models, right? So for Jonas, I was actually at the EOC, I was actually at the Port Authority EOC telling them that, the Emergency Operations Center, explaining through the uncertainty bands that we're seeing, and we're looking at the 95th, but we're tracking the 95th percentile of that uncertainty, by the way, in that situation. Telling them that you are not going to go over what we're actually seeing 2 weeks ago in the previous spring tide that I showed before, right? Based on our uncertainty, based on the model result that we have. So I am very confident that the uncertainty bounds that we have are quite a good predictor of what can happen in terms of, at least in those stations that we have. Now going to the street by street, you're right, there's a lot of other things like sewage backups and so on that we are starting including in the models by coupling hydraulic models of areas to the...
Your mayor, she has a very big responsibility, right?
Right.
Whether to evacuate, not to evacuate, what to do.
Right.
And if she gets it wrong, either way, too high or too low, she's in trouble. So
Right.
it's a big responsibility for
Absolutely.
professionals like us
Right.
to tell them.
That's right. And like I said to National Weather Service, we have National Weather Service people here. First of all, it's not the models, it's the modelers and the forecasters that make the forecast. So that's part of the answer that you have. And all we can provide is the best science we have. All we can provide.
Maybe we should continue this at lunch. Thank you very much.
Everybody is trying to know everything.